All right, problem number 1 on the worksheet says a solid box B is bounded by the planes x equals 0, x equals 1, y equals 0, y equals 2, and z equals 0, z equals 3. Suppose the mass density delta at the point xyz in the box is given by the function delta equals 1 plus xyz. Find the total mass of this solid box. All right, so I have the box pictured up here, and just for emphasis, right, B is a solid box, meaning that the region B includes the surface of the box as well as all points inside the box. Okay, so this density function delta here measures the density at all points on the surface and inside. Okay, and we're going to find the mass of this solid. Okay, I want to just clarify that because sometimes I think there's some confusion as to whether these regions are talking about just the surfaces or the regions inside the surfaces. Okay, and again, when we're talking about solids here in three-dimensional space, it's the surface and what's included within the surfaces. Okay, cool. All right, so now let's go ahead and compute the total mass. So just as we said in the intro video, the mass of our solid box here will be equal to the triple integral of our density function over our region B. Because when you take the density and you multiply it by a little change in volume, that's going to give you a mass, right? It's going to give you the mass in a little differential region within the box, and then this integral is saying, okay, now add up all of those masses as you range over the box, and that's going to give you the total mass. All right, so now let's go ahead and compute this, and as we also saw in the intro video, we can set this up, since we are integrating over a solid box, as an iterated integral. And I'll go ahead and set this up in the order dx, dy, dz. So the z limits would be the outer limits. Then we would have the y limits. Then we're going to have the x limits. And we're integrating the function 1 plus xyz. And then we have dx, dy, dz. Okay, now to compute an integral like this, it works exactly in the same way as a double integral. So if I want to compute, say, the x integral, now y and z are held constant and you integrate with respect to x. So let's go ahead and do that. The x integral here would be x plus x squared over 2. And then we have our yz, and those are held constant. Now evaluate from 0 to 1. And we still have our dy dz. So that's going to give us, well, 1 plus 1/2 yz when I plug 1 in for x. And when I plug 0 in for x, I'm just going to get 0, so that's it. Okay, so now we go ahead and integrate with respect to y. And that's going to give us y plus, integrating y here would give us y squared over 2, and there's a half in front, so that's y squared over 4. And we have our z. And now evaluate from 0 to 2. And so that's going to give us 2 plus, and here I'm going to get 2 squared is 4, over 4 is 1, so I'm just going to get a z. And plugging 0 in for y would give me to 0, so we wind up here, which is pretty simple integral. We're going to get 2z plus z squared over 2. Now evaluate from 0 to 3, so that's going to give us 6 plus, and this is 9 over 2. And so 12 halves and 9 halves is 21 halves. And since there aren't units provided, we'll just leave it as 21 halves. All right, and that's going to be the mass of this solid box. Thanks.